7 years old. That's like me being in my second house.
I'll be collecting two things when the bell rings. I'm going to collect them separately though. I'm going to get your labs first, and then your Cornell notes. Alright, so make sure your name is on your labs first, please. Pass that just by itself to the right side. As I said, I'm going to get the stuff separate. So labs first, please. Make sure your name is on them. Please pass them to the right-hand side as always. Stapling, staplers up there at the desk. The labs first, please. Thank you. Okay, all right, she's stapling. All right, stapled lamps here, I'll take those just directly from you. Also then now go ahead and pass over your Cornell, pass over your Cornell notes to the other side as well, please. Pass over the Cornell notes, please, to the right side.
Yeah, I just have to.
Here, here, and here. All right, let me get all of this organized. This goes to that.
Actually, you want to do it for 4 days ago.
There it is. Sanitation worker. Good. Good. Mission organization. There should be a TLC TV show about this. All right, there we go. Let's go ahead and start with the following term today here at the beginning of the period. Can anybody tell me what this refers to? Does anybody have any idea what this set of expressions or set of variables refers to? No, it refers to the following. Yes, that's right. Six Flags Magic Mountain 6F. It's time for us to start getting ready for our field trip.
Yay!
When is it? It's Wednesday, April 15th.
Is that even at all?
It's a 2-4-6 day. Now, incidentally, this is actually going to occur during standardized testing, and it actually does affect a couple of my students. But I've managed to get those students' standardized testing postponed, such that they can go on the field trip. If you are one of those affected students, I'll be telling you about it much later on when we get closer to the actual day itself. But for now, it's Wednesday, April 15th. It's going to be a 2-4-6 day. I'm going to tell you all the logistics about the day, the actual assignment that we do while we're at the park, etc., when we start getting closer to that date. But the reason why I'm telling you all of this now is because I need your help. We need to start getting ready for this trip. We're going to start getting ready for it and following that.
Wait, there's an assignment like companies that
No, this is not an assignment. Hang on. There will be an assignment for the trip itself. Yes, you guys will be doing the lab exercise while you're at the park and finishing it up afterwards. Excuse me, it is worth 100 points.
I'm so excited.
Sean, come on. Again, but for now, we have to do this.
You'll have to wear matching t-shirts or this.
All right, now, in all seriousness, this trip is very expensive. It's difficult to pull off. The reason why is the following. First of all, each individual ticket is $32 when we get them in bulk in this manner. We do get a discount, but it's 32 bucks per ticket. I have over 180 physics students. Not only do, of course, you guys go, but all the honors classes go, all the regulars, all the AP classes, all 6 of us, we all go together the exact same day. And everybody, by the way, does the exact same assignment, regular, honors, and AP. In addition to paying for the tickets, however, we also have to pay the transportation costs for 4 buses, and we also need to get a couple of substitutes for some of the teachers that serve as chaperones with me and assist me on the trip. Total cost of this trip is $8 grand, and we basically have to raise the money. Now, I go to the Booster Club early in the spring semester. I already have done so. I went to their last meeting in February. They agreed to cover part of the costs. However, there's a caveat. They asked me to specifically ask you guys and your parents to assist with a donation to the cause, if you will. And then at the end, after we go to the trip and total up all the costs and what our bill is, whatever the difference is between donations from parents and students and what we actually have to pay, then the Booster Club assists in that manner. So they do help us pay for this trip, but they do so with this stipulation that I ask you guys for help. Okay, now, in years past, it was actually fairly easy to raise all the money for this trip because there used to be a little bit of money put into the budgets in school for field trips, buses and so forth. And in addition to that, it also used to be really easy to raise money on campus. Not so much, however, anymore. For basically the following reason. You guys ever seen these little candy suitcases that I periodically have lying around? Right now I store things in them. There's wire, for example, in this one here. But where did this little suitcase of candy come from? Well, it came from about 10 years ago when I used to raise money for this trip by having all of my physics students sell candy on campus. I would give each student a box of 40 bars of candy like so. The bell would ring. You'd walk outside, you'd hold the box up, and you'd yell, "I've got candy for sale," and the 9th graders would come down. It was actually very easy to sell a couple of $1,000s worth of candy on campus in a short period of time to raise money for this trip. Not so much anymore though. Reason why, about 10 years ago, the California State Legislature in its infinite wisdom passed a law. The law was that it's actually illegal to sell junk food on school campuses statewide. So that's why there's no soda, for example, in the vending machines. That's why there aren't candy bars in the vending machines, because you're literally violating state law by selling candy on campus. It's a felony. You could sell drugs on campus, but you can't sell candy. Now, when it comes to raising money by selling sweets on campus, some groups try and do it, like they have bake sales and so on and so forth. But where have you noticed they're sitting when they set up their bake sale table? Yeah, they're across the street, they're off campus, because if they were literally on campus, they can get arrested. Now, in addition to this, when the California State Legislature passed this law, they made it really difficult to raise money to do field trips and so forth, because by far that was the easiest way of doing it. I've tried other means of raising the money, like having students sell magazine subscriptions and crap like that, but frankly, it's not worth the effort because you don't get any money that way. So then therefore, I'm forced to do the following. Let's take a look. So given the current economic conditions, that means 2 things. Number 1, I can't raise money on campus by selling candy, and number 2, there is no budgets for field trips anymore. Booster Club is asking me to ask you guys, parents and students, for a donation to assist in covering the admission ticket and transportation costs for all of us to go to Magic Mountain. The trip is scheduled for Wednesday the 15th. The cost of each admission ticket is $32, and the Booster Club has asked for as many donations as possible. As I said, we also have to pay for 4 buses and subs for a few teachers that serve as chaperones. Students and or parents may contribute as much as they wish. As incentive, students that donate towards the trip will receive 25 points of extra credit. There's no other way for me to do this. There's really no way around it. Now, when it comes to the extra credit, I'll dump it right into your grade as soon as the donation comes in. I'm not going to wait until the end of the year to do it. I'll just dump it in immediately. Students and parents, of course, are not required to donate funds, and more opportunities to make up for it for extra credit will appear later this semester. Now, if you already have a season pass or multiple passes to the park, show me, because that's less tickets that I then have to buy. So then therefore you'll get extra credit in that manner if you already have your own pass or multiple passes. Now, if you choose to donate, please do so. We're going to do this legitimately, that is, as a check written out to Palisades Charter High School. Don't give me cash. It's just harder to keep a paper trail that way. And don't make out a check to me. Make it out to Palisades Charter High School, because that's what I'm going to do. And I have it right here. I'm going to give you a receipt from the school where on the receipt is the school's federal tax ID number. So then later on, when your parents file their taxes for next year, they can then obtain a tax deduction properly by donating in this manner. But this is basically what we have to do. We have to raise money in this manner by getting donations from Booster Club and from parents in order to pull this trip off, because it's so expensive. There's really no other way to do it. Yeah.
The admission ticket itself,
We get the tickets in bulk, that's why
Okay.
there's a big discount. So the way that Magic Mountain does this is actually really nice. They actually send me 200 tickets ahead of time. They're actually sending me 200 tickets this week. We then go to the park that day with our tickets. Whatever our unused tickets are, I turn them back into the park, and then they bill me for the stuff that we actually did use. So this is what's termed as being on consignment. So that's how Magic Mountain does it. They make it really easy for teachers and so forth to do the trip in this manner, but it is still obviously very expensive to pull this off.
but
Yeah.
the admission ticket, are we gonna give that to you in check, or what's the deal with that?
No, donation, should you choose to
Right,
do
it's the
so,
check.
basically just goes into covering everything. I have to cover everything. I have to cover not just admission costs for that, but for tickets, but I also have to cover buses and so forth. As I said, the Booster Club helps out. They do
Okay.
so substantially, but their stipulation is that I have to specifically ask students and parents for donations. That's kind of like their criteria for helping out here. Yes?
So that day we come to school and we need to go?
No, we actually don't leave campus until about 9:30 that morning, because the park itself doesn't even open until 10:30. Okay, then we get to the park, we're at the park all day, and then we come back here before the late buses leave around 5:30 in the afternoon. But it is still basically an all-day event. I'll tell you much more about the logistics when we get a lot closer to the day. So it's still more than a month away, but I have to start raising the money now, okay? Yeah.
For the donation, is it, do we have to donate like 32 full time?
No, whatever you think is appropriate, that's perfectly fine. In other words, whatever you think you is worth it, then I'll take it. That's basically what it boils down to, okay?
Is there an average amount that people have donated in the past?
Whatever you feel is appropriate. Whatever you feel is appropriate. But we do have to raise this money, okay? John?
In regards to that law that was passed, how come the schools permitted to sell cookies and like other stuff like
Because
that?
when they're talking about junk food, they're specifically talking about like candy bars and soda in particular.
They also have soda and vending machines.
And also about like, the bake sales and so forth. They're off campus. No, when you go to the vending machines here and buy soda, you're not buying soda, you're buying Powerade, which is still frankly
They
junk.
have like.
They
gotta have
there's a timer, so like.
Oh, that's right, but it's not during school hours, that's
Yeah.
correct. It has to be after 3:08. So that's what that timer is all about, yeah, absolutely. Yeah, so if you were ever wondering that, it's specifically because of that law. It's not necessarily our school's policy for that, that's state law. As crazy as that sounds, yeah.
If I hypothetically started selling candy like illegally, like.
I tried it, I did it one year where the administration was like, nah, you can't do that, because if we get audited, we get red flagged.
I see.
You can't do it. Yeah, I've tried my way around it.
But what would the consequences be for me?
Consequences for you would probably be minimal, but the school can get fined,
Okay.
and I certainly don't want to get that.
So kids that like sold candies, like, was that, because I mean like last year. when I
If it was for an official school function, it was illegal.
No, they were just like on the side, like,
I mean, if they're off campus across the street, that's one thing.
in school.
But no, they can't do that, that's illegal.
I think.
And if the school got caught, we got audited for it, for example, we can get fined. Technically, it's violating state law.
Are you serious?
All right, put this aside, please, take out your notes.
You don't want to raise your hand and ask it? Okay.
All right, we are getting to the tail end here of this current unit on oscillations. We essentially have one more major topic here to cover, and that's today, what's called resonance. Next time on Wednesday of this week, we review for the next exam, which is Friday. Now, yes, I understand a lot of you have a big Gov test coming up this week, but that's just the way it is. Okay? All right, let's go ahead and get to it. Okay, everybody here has heard of the word resonance, but of course it refers to a specific type of physical phenomenon. Now I'm going to demonstrate it to you a number of different ways today. I'm going to begin in the following manner. Okay, what I'm going to have here is a simple pendulum. And for now, the simple pendulum here is oscillating back and forth with its own natural frequency. Remember from last time in class, we start to refer to this as omega naught. So I'm going to begin in the following manner. begin with a simple harmonic oscillator with natural frequency omega naught. Okay, then what I'm going to do by means of these rubber bands that you see right here is exert what is called an outside driving force on the pendulum. I'm basically going to take a series of rubber bands here and yank back and forth like so and exert an outside force on the oscillator. When this occurs, you end up with what is called a forced oscillator. So now, an outside that is external to the pendulum itself, an outside driving force, as it's called, is exerted upon the oscillator, resulting in what is called a forced oscillator. Okay, now there's going to be a couple of simple properties associated with this outside force. Okay, first is the maximum amount. The maximum amount of yank, if you will, that I could apply like so by yanking on the pendulum in this manner by means of the rubber bands. This is referred to simply as capital F naught. So the maximum value of the force that I can exert called F naught, but it's the second property that's the most important. What I'll do is I'll yank back and forth here on the pendulum by just moving my hand back and forth like so, and when I do, there's a frequency associated with my hand. This is referred to as the driving frequency. So this second property of this outside force called the driving frequency, that's the frequency of my hand going back and forth, that's referred to as omega. Now just to clarify what's what here. The omega naught has to do with the oscillator itself. That's just this natural frequency. The omega is from me moving my hand back and forth. That's this outside driving frequency associated with this force. Mathematically, we can easily describe the force that I'm going to exert on the oscillator, by the way, as just a cosine. Like so. So it's just me moving my hand back and forth as I exert the force on the pendulum by means of the rubber bands. Okay, now what I'm going to do is I'm going to kind of play around the variables here of how I exert the force on the pendulum, and let's just observe the behavior. Primarily what I'm going to be manipulating here is the value of omega, the driving frequency of my hand going back and forth. What I'll do is I'll start with a low value of omega, a low value of the driving frequency. And when I do this, like so, not much happens. Pendulum just kind of jiggles in place a little bit, and that's about it. Watch what happens at high values of frequency. So now I'm going to make the value of omega a large value, so I'm going to just rapidly move my hand back and forth. And once again, basically not much happens. The pendulum jiggles around a little bit, but nothing interesting is occurring. And now lastly, watch what happens if I move my hand back and forth with a driving frequency of a very specific value. Even if the value of F naught, the maximum amount of force, is low, watch what happens. So now I'm barely yanking back and forth like so on the pendulum, but when I do, the frequency of the driving force from my hand is at a very specific value. And when this occurs, notice that the amplitude of the oscillation is getting really large. We say that the oscillator is resonating. Now, pretty obviously, what do you know about the frequency of my hand going back and forth and the natural frequency of the oscillator itself? Yeah, they're obviously equal to each other. This phenomenon is referred to as resonance. So note it in the following way. When the driving frequency omega matches up with the natural frequency omega naught of the oscillator itself, very large amplitude oscillations occur. we say that the oscillator, the forced oscillator, is resonating. Now let me show you more or less the same demonstration, but in this case in a slightly different manner. And when you see it in this manner and compare it to your own experience, for example, in the playground, this is going to look very familiar. So what I'll do in this case is take the rubber band off, like so. Greg. That's for you. And then I'm just going to reattach like this. And then I'll just set the pendulum here into motion. It will oscillate back and forth with its natural frequency, etc., etc. But now I'm going to exert the outside force on the pendulum by just doing this. The amount of push, that is F naught, that I exert here on the oscillator is quite small. But if the frequency of my push, omega, is the same as the natural frequency of the oscillator itself, omega naught, then the pendulum resonates. So in this case, I was only using a small amount of force, like so, upon the pendulum. But when I do this at the same point in the oscillation every time, that is in phase with a frequency that's the same as the natural frequency of the pendulum itself, then it resonates. Now obviously, which piece of playground equipment that you're familiar with since your own childhood am I showing here? Swing. Yeah, it's obviously a swing. So in the case of a swing, you're sitting on the swing, and let's say you're not moving. Okay, and then we set you into oscillation like so, and you oscillate back and forth at your natural frequency. However, if you've got a person behind you that is pushing on you to keep an oscillation, does that person behind you have to push really hard?
No.
Absolutely not. They barely touch you. But as long as that push is in phase with your oscillation, and it's also of a frequency that's exactly the same as the natural frequency of the pendulum itself, then you're going to resonate. Now you could of course do this your own, or do this by yourselves on a swing. You probably have been doing this since you were 3 or 4 years old by doing what?
Pumping.
Yeah, by tucking your legs back and forth when you're on the swing. Because when you do that, by shifting your body weight in this manner, you shift your body weight and swing your legs back and forth with a frequency that's the same as the natural frequency of the oscillator itself, thereby resulting in large amplitude oscillations. Therefore, you start to resonate. So you actually have been already intuitively familiar with the physical principle of resonance, even when you were as little as 3 or 4 years old, by causing yourself to resonate on a swing set, for example. Now, how do we show all of this mathematically? Actually, fairly easily. Here's how this is described. Now, as I describe this mathematically, even though I've been using a pendulum here to demonstrate just because it's really easy to do, let's assume that our oscillator is just a mass attached to a string. It's just a little bit easier to see the math in this manner. So for resonance now, mathematically, what we want to do is explain why the amplitude is so large. When omega matches up with omega naught. Omega being the driving frequency, matches up with the natural frequency, omega naught. Now here's how we set up F equals ma for specifically the case of the forced simple harmonic oscillator. Okay, we still have the spring force, minus kx, but now we have this outside driving force, which if you recall I wrote down earlier in the following way. So these two forces then added together give us mass times acceleration. And we end up with yet another differential equation, and we want to solve this differential equation. This one actually turns out to be really easy to do. Okay, as is always the case when solving this differential equation, the first thing I do is just divide the mass out to both sides. Like so. And then before I write out the solution to this differential equation, let's recognize something right here. Notice that this right here, k over m, is the natural frequency squared. This right here is omega naught squared. Let's just go ahead and write it in. here's our differential equation. So then how do we describe the solution to this differential equation? Well, the solution, once again, is a position equation, the position of the forced oscillator as a function of time. But describing the solution here is actually quite easy. The solution is actually just nothing more than a basic cosine. Like so, where A is the amplitude, and in this case, this is what we're interested in describing. And this omega right here, by the way, is not omega naught, the natural frequency of the oscillator. This is the driving frequency of my hand back and forth, the omega. Okay, now why is this the solution, and why does this give us the behavior that we saw? Well, what I'm going to do is take the position x here, the solution, and plug it into here. In just a moment, I'll take its second derivative, plug it into here, and then we'll just kind of see what happens. Okay, now differentiating first. If I differentiate it once with respect to time, it basically looks like a velocity expression, like so. Differentiate it again to get an acceleration expression. Looks like this. And then this here that I just wrote down last, this second derivative, that's what goes into the right-hand side of the equation at the bottom of the top four. So now let's plug into the differential equation itself. So when I plug into the differential equation, I first of all have my first term, which is negative omega naught squared, multiplied then by the position x, like so. Okay, then I have the middle term there with the outside force that's completely untouched in this process. And then lastly, on the right-hand side is the second derivative, which is this expression here. Like so. Okay, now as is always the case when setting up these types of differential equations, the cosine term cancels out. Here, here, and here. But notice what doesn't cancel. What doesn't cancel is the amplitude, A. So now the last step here is to solve for the amplitude A. And when we do, we're going to end up with a description of the amplitude A in terms of the driving frequency omega. We're going to end up here with a function. Now, just to do the rest of the math, what I'm going to do is take this negative omega naught squared A, move it to the right-hand side of the expression. So when I do, I have the following. First of all, F naught over M. And now on the right-hand side, I'm going to have A times omega naught squared minus A times omega squared, like so. Okay, then I'm going to switch to these boards over here for now. Notice that I can factor out an A from each term there on the right-hand side, and then I'll just do a little bit of division, lastly, for the last step, to get a description of the amplitude A as a function of the driving frequency omega. That will then give us the following. So first, just factoring a little bit on the right-hand side, like so, gives us this. And now divide by the parentheses on both sides to get A by itself. And you end up with this. So, you end up with A, the amplitude that is, as a function specifically of the driving frequency omega. And let me write it as such, like so, here on the left-hand side of the expression. Okay, now notice the behavior of the denominator of this expression. For example, when the driving frequency omega gets really close to the natural frequency omega naught, the denominator here is very small. If the denominator is small, what can you then say about the amplitude? That it gets really large. So we're starting to see that behavior here mathematically in the function itself. Now before I go through the complete description of what this expression here is saying, there is one more added detail that we add to this. If omega, the driving frequency here, is bigger than omega naught, the natural frequency, in the parentheses you end up with a negative number. In the context of the amplitude, that has no meaning. So to get rid of negative signs here, usually what we do with this function is square this term right here, and then take the square root of it. So this just eliminates negative signs which have no meaning in this context. So that's why you're going to see the function written this way. The easiest way to understand what this function is saying is to actually graph it out. That is, graph the amplitude here as a function of the driving frequency omega, or right here, the natural frequency omega naught. Because notice what happens to the denominator of the expression if the driving frequency omega is the same as the natural frequency omega naught. It's equal to 0. And if you end up with 0 in the denominator, this then means that the amplitude is literally undefined. On this graph, it corresponds to an asymptote, like so. And now let's just look at either side of the asymptotes. Here's how I'll do that. I'm going to switch my pendulum back here, by the way, to this situation involving the rubber band, because it's just really easy to do that way. And then what I'll do is, once again, play around with the value of omega, that is the driving frequency of my hand going back and forth. So let's start with the left-hand side of that asymptote, where omega, the driving frequency, would be really small. So in other words, I just do something like this. Notice that the frequency of my hand going back and forth is very small, and basically the pendulum just kind of jiggles around a little bit in place, and that's about it. So nothing special happens over here on the left-hand side of the asymptote. You basically have a small value of amplitude. But then, as I get closer and closer to the natural frequency of the pendulum itself, boom, now you're starting to see the approach towards the asymptote, and the amplitude is getting larger and larger. So then therefore, the left-hand side of the graph approaches the asymptote like so. Nathan, stay with me. And then it comes down on the other side of the graph in the following way. So now on the right-hand side of the graph, we'll make the omega really large. And once again, the amplitude is small. It's basically just jiggling in place. So on the other side of the asymptote, the graph comes down again like so to give you a low amplitude associated with the oscillation. So in a demonstration, what you're basically starting to see is this portion of the graph corresponding to resonance. Now for this equation, which as I said earlier corresponds to the forced simple harmonic oscillator, it literally is an infinitely big amplitude when the driving frequency matches up exactly with the natural frequency. So why didn't that happen here? Well, the reason why it didn't happen is because there's no such thing as a simple harmonic oscillator. There's only a damped harmonic oscillator. When you take damping into account, as you'll see, there's an additional term that appears here in the denominator of the expression, and it turns this asymptote into a finite peak, as we say. In other words, the graph itself ends up with a finite point here at the top, and then comes back down. It basically looks like this. Okay, without plowing through all the necessary math, when you do take damping into account, so you then have what is called the forced DHO. And the equation that describes the amplitude here looks much the same as what I wrote up on the top board, but there is an additional term that appears here underneath the radical in the denominator. You still get this stuff here, and this stuff here is the most important part. But there's an additional term due to the damping that appears mathematically in the following way. I'm just quoting this, I'm not going through all the necessary differential equations that shows this directly. But essentially what it does to the graph above is it turns that asymptote into a finite resonant peak, as it's called. You basically end up with a curve that looks like this, using the same colors. So amplitude as a function of omega. It turns out that mathematically it's not quite when the driving frequency matches up with the natural frequency. It's pretty close, but not exact. But that's basically where the peak occurs. You end up with something that looks like that. So this right here is referred to as a resonant peak. That's what you're seeing in this demonstration. So the resonant peak then occurs more or less when the driving frequency of my hand going back and forth matches up with the natural frequency of the oscillator itself. Another obvious example of this is, of course, the swing set, like I described earlier. Okay, let me show you a few more examples of resonance. There's some stuff out of the way here. Okay, next, let me show you this little device right here. This some of you may have seen before because it's been sitting on the side counter for the last few weeks. It may not look like much, but this series of pendulums here is actually a very primitive ancestor of this. It's actually a very primitive type of communications device. And what I'm literally going to do with this device is I'm going to send a message from one side of it to the other. The way that I'm going to do that is as follows. This pendulum right here has a certain length associated with it, and I'm going to refer to this as my transmitter pendulum. When I set this pendulum here into oscillation, it will oscillate back and forth with its natural frequency. As it does, it actually causes this metal cylinder, which is sitting here on two nails, one here and one here, to twist, like so. And the frequency of that twisting cylinder is going to be exactly the same as the natural frequency of this pendulum that sets it into motion in the first place. And then this twisting cylinder here oscillating back and forth with that frequency, well, that is then going to be an outside driving force on these other two pendulums, like so. And if the frequency of this twisting cylinder matches up with the natural frequency of one of the other pendulums, then one of the other pendulums is going to resonate. The reason for it is because its natural frequency, this receiver pendulum here, is going to be the same as the frequency of the driving force as this cylinder oscillates when it was originally set into motion by this pendulum here. So it's kind of like a two-step process, if you will. This transmitter pendulum causes this cylinder to twist, and it does so at a frequency equal to the natural frequency of this pendulum. And then the second part of the process is that this twisting cylinder exerts an outside force on the other pendulums. If one of the other pendulums, obviously this one here of the same length as this one, has a frequency that matches up with that of the twisting cylinder, then it's going to begin to resonate. Then what I could do is ahead of time, I could set up some sort of a code or a system. I could say that a specific amplitude of motion corresponds to a piece of information, like a letter of text, say the letter A. So now what I'm going to do is send the letter A from my transmitter pendulum here on my right to my receiver pendulum here on my left. In order for this to work, however, these two pendulums have to be of the exact same length. I can control, for example, the length of this pendulum by raising the string up and down appropriately with this alligator clip. But what I have to do is get those pendulums' lengths to match up exactly before the process begins. There we go. A little bit more. Well, like so. And then I get these guys as still as I can. That. And now I'm going to send the letter A from the pendulum on my right to the pendulum on my left. Like so. And now notice the pendulum on my left is beginning to oscillate with the same amplitude as the original transmitter pendulum had on my right-hand side, thereby meaning that I have sent the letter A, for example, from the pendulum on my right to the pendulum here on my left. Henry?
If these were actually used for communication, how long would the tube be?
Yeah, so notice that there are some major disadvantages to doing this mechanically. Okay, one major disadvantage is the amount of damping that's occurring here. So very quickly, the energy is just going to get burnt out as heat. So even though, yeah, I can send a message from one side of the pendulum or the apparatus to the other, I'm only covering a distance here of about 6 inches or so. It's doubtful that I'd be able to do this even as far as across the room because the energy would damp out as heat almost immediately. So this is one of the reasons why we don't have metal cylinders with pendulums hanging from them stretched all the way around the world to send messages back and forth because number one, the energy damps out as heat, but a little bit more importantly, number two, the speed of the transmission of the information here is really slow. It took about 30 seconds for the information to basically travel a distance of about 6 inches. And then once again, you can see that if I resend the message from my transmitter here to my receiver on my left, and it takes about 30 seconds or so for the receiver on my left here to begin to oscillate with the same original amplitude as that of the transmitter over here on this side. So the speed of the transmission of the information itself here is obviously very small. Yeah.
So what is the shorter pendulum?
Okay, this guy right here, of obviously a different length than the others, has a much different natural frequency. Notice he's not resonating. He's just kind of jiggling around a little bit. So I put him there as a means of demonstrating that you can only send a message from basically one pendulum to an identical pendulum over here on my left. So of course, we don't send information like this mechanically. Instead, we do it electronically. How is it done electronically? Well, picture two phones as walkie-talkies. If you think of it that way, then the process is actually more straightforward. Because what you do is you first of all speak into the transmitter phone. When you speak into the transmitter phone, the frequency of the sound from your voice via something called Faraday's law is converted into an electronic signal within the phone itself. It specifically sets up an electrical current within the phone. The frequency of that current is exactly the same as the frequency associated with my voice as I speak into the phone. And then that current, which is oscillating back and forth within the circuit of the phone itself, gives off radio waves. It gives off radio waves of the exact same frequency. And then those radio waves act as the driving force on another phone, the receiver phone. So when those radio waves hit the receiver phone, that then sets up inside the receiver phone an alternating electrical current of the exact same frequency. And then using Faraday's law in this case in reverse, once again, you then convert that electronic frequency into a sound frequency that is a wave that then comes from the transmitter phone to the receiver, and then you hear your friend's voice out the other side. So it's basically the exact same process as this in principle, but the advantages to doing this electronically are twofold. Number one, the amount of damping is next to nothing, so you don't lose a lot of energy in doing it in this manner. And then number two, it's the speed of the transmission of the information. It's the speed of radio waves, which is the speed of light. So that's how we do it electronically. You basically convert a sound signal into an electronic signal, transmit that electronic signal by using radio waves, and then do the process backwards out on the other side. But it all uses, once again, the same physical principle, which is resonance. So this is not magic, this is physics. Okay, let's take a short break before we go. Yeah. Nathan, you gotta stay with me, come on. Time changes be damned, come on.
Use that plate, study.
Right, and it's a vacuum inside. So that's thickness is charge distributed over a cylindrical shell. So this is all charge, it's all charge. Yeah, the charge density rho is charge per volume.
It takes place in the pancake.
That's what he's on.
Yeah, you're on the right track. Okay, so how do you write an expression for volume in terms of what I gave you?
Okay.
Okay, you're on the right track.
You can do it.
I know, but like, we'll just take it back to it. He has to. He hears already.
Yeah, and we just did it.
You guys did go spring break. I'm gonna do here tomorrow.
Mr. Shaw,
First semester senior.
how long until spring break?
This week, next week, and then 4 days.
Oh,
Yes, we still have a ways to go till spring break.
That's not
that's not bad at all.
Next week.
Wait, next week?
Yes, but there's more time between now and spring break than spring break itself. Considerably.
So,
That's okay. That's okay, Mr. Tyler.
Doesn't mean
Just
we can't, like,
hope that it's
there's more
there.
time between now and the weekend, but I'm still looking forward to the weekend.
It's only 7 days more. It's only
spring break is 11 days.
It's amazing how much time we all spend calculating out all this nonsense. When I was in graduate school, when I was in college and in graduate school, we would start keeping track of the end of the terms like months in advance in terms of the seconds. Yeah, this is a tough time of year. It's a long slog between now and the spring
It
break.
really is.
But then after spring break, especially seniors, it goes lightning fast.
Can I pay you to take my gun test?
No, that really, that wouldn't be good,
Come
John.
on, how hard can it be? All right, one more and then I gotta.
It's,
This area
don't do that.
I'm
Yeah.
It's
Come on, you walk in, you sit down, you take the test, you get up and you leave.
I know, but like.
How hard can it be? You can't miss.
It's annoying.
This
This is like
you
the
don't
hardest
You
work
can't
I've
miss.
ever
How hard can it be?
That's the hard
It
part.
should take you 5 minutes.
subject is so
I had to write, I think I put, I did 2 effort, 2 to write.
It should take you 5
80,
minutes.
wait, is it 80 or 50?
60.
5 minutes.
Yeah, 5 minutes.
Yeah.
3 minutes for the whole choice and then 2 minutes for the.
Nathan, do me a favor. Let's clear your desk, clear your stuff out of the way, including your backpack underneath. Okay, in part, this is designed to get Nathan moving here.
Almost go with weights and then watch long.
No, chairs are fine.
I wish.
watch
Are you
ball.
guys-
I'm getting to that in a few minutes, all right? All right, guys, wake up. Let me go ahead and move on. Come on, time changes be damned. All right, wake up, come on.
Hello.
Couple of more demonstrations of resonance. Before I get to what's in the back, guys, before I get to what's in the back, let me show you kind of like a slightly different version of the same demo that you saw. But instead of using pendulums to resonate, I'm going to use the chairs here instead. I'm going to send a message from one chair to the other. And here's how it's going to work. If I arrange the chair like this and set it into oscillation, this physical pendulum, as it's called, this example of a physical pendulum, as it's called, oscillates back and forth with its own natural frequency. Now, when it does oscillate back and forth, you're certainly not going to be able to see it because the table is so rigid. But like with the metal cylinder and the other apparatus, right now the table is kind of twisting slightly. You're never going to see it because the table is so rigid. But the twisting of the table, it does so at the same frequency as the natural frequency here of this pendulum. And then if I have a second chair, this one here that is identical to the first, and I set this up before the day began today, by the way. If I have another chair here that has the same natural frequency as the natural frequency of this first chair, then like with the pendulum demonstration from a few minutes ago, I can send a message from one chair to the other. Now the amount of resonance that occurs here is very small, by the way. You're not going to see this chair, for example, like fly across the room with this huge amplitude. And the reason for that is because the rigidity of the desk gives us a lot of damping. So most of the energy just damps out as heat immediately because the desk is so rigid. But I can get the chairs to resonate a little bit by basically doing the following. Now, the easiest way to see this, by the way, is for you to take a look at the feet of the chair here on my right against the floor. So you'll then be able to easily see the motion in that manner. Okay, I got the chairs as still as I could. And then I take my transmitter chair here on my left and I set that into oscillation like so. And now watch the feet of my receiver chair here on my right-hand side. See the feet there against the floor beginning to move a little bit? Like so. So it's basically the same demo as the pendulum. It's just in this case, the amount of damping is just a lot larger. So I'm getting this chair here to send a message to this chair here on my right. So you can try this with your own dining room set, for example, at home. See if you can get your dining room set at home to resonate. That's kind of cute. Okay, and now, starting to look ahead a little bit into our next unit. After we complete this unit on oscillations, the next most natural unit to get into is waves. Because waves, as you'll see, are traveling or propagating oscillations. One very important type of wave that we'll look at is a sound wave. A sound wave is a specific type of wave. It is once again a traveling oscillation. And then one of the things that we'll do as an application within this unit on waves and sound is we'll take a look at the basic physics of musical instruments. When it comes to musical instruments, the basic physics begins with resonance. I'm going to begin to demonstrate it here in the following manner. Okay, here's a wine glass. If I strike the wine glass like so, the wine glass oscillates back and forth at its natural frequency. When it does oscillate back and forth at its natural frequency, it brushes up against the air that's immediately next to it, causing sound waves to propagate through the air. The frequency of the sound waves is exactly the same as the natural frequency of the wine glass yourself, that you're hearing, that is. So then therefore, when you strike the wine glass, it sets the air into vibration immediately around it with the exact same frequency, and that's why you can hear it. Yes?
Is that why when you like take your finger and when you like?
That's another example of resonance, but I'm going to be doing something slightly different here.
Okay.
So what I'm going to do is I'm going to force this oscillator, but in this case not by hitting it, like so, but instead by using additional sound waves. What I'm going to do by means of a speaker there in the back of the room is I'm going to have sound waves hit this wine glass. And if those sound waves coming out of the speaker have the same frequency as the natural frequency of the wine glass itself, then the wine glass is actually going to begin to resonate. Now, how many of you have seen video footage of engineers setting up a demonstration like this where the wine glass itself actually shatters? Okay, that is possible to do, but it turns out that the sound that's hitting it has to be really loud, and I lack the ability to do that here in the back of the room, but I can get the wine glass to noticeably resonate. So here's then what happens.
Whoa.
I yell at the wine glass
Yeah. High pitch. You know, like this thing.
All right, basically what I have here at the back of the room are two things. Okay, the first thing that I have right here is what's called a function generator. Function generator is able to generate pure tones, sounds of just a single frequency. That's done electronically. The output then comes out of the speaker here. Basically what a speaker does is it uses something called Faraday's law to convert an electronic signal into an audio signal, a signal of sound. And then right over here is basically the process in reverse. Right over here is a microphone, and what the microphone does is it takes a sound wave, an audio source, and then through Faraday's law it converts it back into an electronic signal. And then the output of that signal you can see here on this screen. This device is called an oscilloscope, an oscillator scope. So when I speak into the microphone like this and you see this complicated waveform appear on the screen of the oscilloscope, it's because when I speak to you with my voice, it's like you're hearing a range of frequencies. So it's definitely not a pure tone. Okay, now I'm going to go ahead and turn this on, and after it warms up, this is really old. After it warms up then, the tone that you'll hear coming out of the speaker here is just of one specific frequency, the output of which we can then see on the screen right here. Okay, now what I'm going to do is move the frequency lower like so, and now I'm going to take the wine glass and place it right there in between the speaker and the microphone. And then I'm going to adjust the frequency. I'm not going to adjust the volume, I'm going to adjust the frequency. I'm going to raise the frequency of the sound, the pitch that you're hearing, until it matches up with the wine glass. I'll know that I've matched the wine glass when the waveform that you see here on the oscilloscope screen starts to become still, but a little bit more importantly, you're actually going to hear a difference in the volume. The reason why is because you're going to be hearing two sources of sound, the speaker and the sound coming from the wine glass itself. Here's then what occurs. And then right about there, maybe a little bit less. Right about there. Because listen to what occurs if I take the glass away. And now listen what happens when I put it back. like so. That slight change, not in pitch, but it's a slight change in volume that you're hearing is because when I put the wine glass there, it is also causing a sound wave. So you're hearing two sources of sound here of the same frequency. What's coming out of the speaker and the wine glass itself. If I strike it and listen, notice they match up. Like so. So then therefore, if I put the wine glass like this, take it away, you're hearing a slight change in volume because when it's there, it's two sources of sound as opposed to just one here by itself. Now, what does this have to do with musical instruments? Kind of looking ahead a little bit into the next unit. Well, when you play an acoustical instrument, and by the way, this is just for acoustical instruments. Electronic instruments is a whole nother ballgame. But when you play an acoustical instrument, basically what you do when playing a note is you somehow set the instrument into vibration. This is done by either hitting the instrument, like with a drum, that's the obvious, most easiest way of doing it, of course, or by plucking or bowing a string, hitting a key on a keyboard, which by the way trips a hammer, which also hits a string, a piano wire, for example. So technically speaking, keyboard instruments are stringed instruments. And then in the case of a brass or a woodwind instrument, you set the instrument into vibration by just blowing into it. But regardless of how you set the instrument into vibration then, the following happens. Built into the instrument is a chamber called a sound box or a resonant chamber, where the vibrating instrument causes the air inside the chamber to resonate. It creates a waveform with a very large amplitude, resulting in a nice, loud, clear tone, which you can then hear. So the basic physical principle upon which music is built, essentially, is by having your instrument resonate equally with every note that you play. So you know that you have a well-made instrument. Sounds perfect, in other words, with every note that's played, because it's resonating the exact same way with every note that is played. When an instrument is out of tune, one of the reasons why it doesn't quite sound right is not because necessarily the frequency is unpleasant. It's just that it's not really resonating properly. It's not producing a nice, loud, clear tone like it does when it is in tune. And then when you play scales and octaves upon which music is based, these are all basically multiples of resonant frequencies. So the opening physical principle in understanding how music is constructed has to do with the physics of resonance. This was all figured out initially through trial and error over hundreds and thousands of years, but now we understand the acoustical physics behind this perfectly. Yeah, she had a question a few moments ago.
Have you ever tried using that thing around a dog?
Well, later on when we start talking about specific types of frequencies, if we wanted to, we could turn this into a dog whistle, and I will actually do that as a demo in about a week or so. Okay? Moving on from there. Yeah, I can show you guys actually a second mechanical universe here in this unit. The one on resonance is actually really good. It's one of the best of the bunch.
You guys take care of
As you
your
see, there's lots of stuff for our students here.
I think it's going to be in June.
I took the ACT, got about 8.
Do any examples?
Third grade.
No, resonance basically is an example itself.
The second one.
Good job.
Same as you. That's really great. Did you specialist?
Yeah, I did this program called Elite.
Oh yeah.
And then I only did one course after that.